Let's have a look at questions 7 through 10. 7 through 10 on worksheet number 3. This relates to our position time graphs. I'm going to ask you a couple lead-in questions to this first. Questions that aren't actually asked on this worksheet, but questions that we need to still know the answer to, whether we're being quizzed on it on the worksheet or not here. This graph is titled position versus time. It should be, because we always put y-axis versus x-axis, right? If you notice, on the y-axis is position, and on the x-axis, it's time. It's always y-axis versus x-axis. Which variable, if I was to ask you to identify the manipulated variable, the variable, not necessarily, sometimes teachers define a manipulated variable as the variable that we change, the variable that you change. That's not necessarily the case. It's the variable that causes change. Does that make sense? What's the manipulated variable in this case? The one variable that will cause something else to change. Parker? Yeah. You're not changing the time. You're not changing the time. Time goes by no matter what. But the change in time results in a different position. Does that make sense? So it's the time that's causing the change. So the time is the manipulated variable, and the position would be the responding variable. How do you know? Just by looking at the graph. Like maybe you know that time is the manipulated variable because you know what a manipulated variable is. But how do you know just by looking at the graph? Is your head up? No? Go ahead. Yeah. The manipulated variable is always on the x-axis. So no matter what graph you plot this year in Physics 20 or next year in Physics 30, the manipulated variable is always on the x-axis. All right. Tell me what the different shapes here mean. I've got a position versus time. I've got the position sloping downwards here, for initially at least sloping downwards. What does that tell us about what's going on here, what the motion of the object in this graph is? Yeah, good. It's a constant negative velocity. Now, be careful here. Okay, this can be tricky because we have our y-axis as a position to the west. We're defining west as positive here, right? Look, it says west, and all these numbers are positive. So constant negative velocity would actually mean constant velocity to the east. Does that make sense? Since it's a constant negative western velocity, it's a constant velocity to the east. What about this one? What about the second one? Constant velocity, straight line, right? Constant velocity. Or another name for constant velocity is uniform motion. Uniform motion or constant velocity. This would be a positive value, which would mean in this case that it would be a constant velocity to the west. Right? Good? All right, let's take a look at the questions that are asked here. Calculate the displacement of the object between 0 and 10 seconds. How do we define displacement? We did this on day 1 of Physics 20. We defined displacement as change in position, yeah. And how do you find position on a position time graph? How do you find velocity on a velocity time graph? How do you find force on a force time graph? How do you find momentum on a momentum time graph? How do you find anything when it appears on the y-axis? Yeah? Yeah, you go up and over. So position, up and over. Displacement is up and over, subtract the two of them. It's final position minus initial position. The final position here at 10 seconds, there's not really any up to do because you're already there, right? 10 seconds, the position is 0 meters. The final position is 0 meters. What's the initial position at 0 seconds? What's our interval there? 10, 11, 12, 13, 14? Going up by ones? So my change in position or my displacement is negative 14 meters. Negative 14 to the west, which means 14 to the east. Now, you write negative 14, that's fine. Okay, on tomorrow's quiz, that would be 100% for that question. But you could have written positive 14 to the east. That would be equally as correct. Okay, what about the displacement between 10 seconds and 18 seconds? Well, again, up and over, and subtract them. Final position minus initial position. At 18 seconds, we got 15. Are we going up by ones here? 10, 11, 12, 13, 14, 15. Yeah. 15, 16, 17, 18. Go up and over That's going to be 6 meters minus 0 meters is my initial position. Positive 6. What does that mean? 6 to the west. In this case, because positive is west. Good. What's the average velocity between 10 and 18? Average velocity is always found the same way. Average velocity. Goes back to day 2. Day 2, physics 20. Average velocity or constant velocity. Yep. Yeah, the total displacement or over the total time. Now, as it turns out, if it's just a straight line, and it is between 10 and 18 seconds, V equals d over t is the same thing as finding the slope, rise over run. So you can think of it either way if you want, but displacement over time will always work for you there. The displacement we already found, it's 6 meters divided by the time of 8 seconds, which gives me 0.75 meters per second. It's positive, which means it's to the west. And finally, the average velocity between 0 and 18 seconds. Displacement divided by time again. What's the position at 18 seconds? 15, 16, 17, 18. 6 meters. The position at 0 seconds is 14 meters. Over the time interval is 18 seconds. That's negative 8 over 18, negative 4 over 9, negative 0.44. What does a negative mean? It's to the east, right? Does it make sense that the average velocity, look, we go east and then we go west. Does it make sense here that the average is to the east? How come? How come? Yeah. Yeah. Yeah, look at the graph. We went east more than we went west. So on average, it's going to be east, right? If I drive to northern Calgary from here, that's a positive velocity. And then I turn around and drive partway back, maybe just to downtown Calgary, my average velocity will still be to the north, right? Even though I had some south velocity, my average will still be to the north because I went north for a lot longer than I went south. Yep, Parker?
Did you find the average velocity by just doing rise over run of the upper and lower other than 8?
And then add them up and divide by 2? No.
Well, it's like at the like so for the upper.
All right, I'm going to hand out fake quiz number 3 then. It's somewhat like the question that we just worked on. We'll give you fake quiz number 3, take a look at it, see how it goes. We'll mark it as a group, just doesn't count for any marks. Tomorrow's quiz that we have for real is going to be much like this. Just a couple little typos on this quiz before you get going on it. On this practice quiz, that is, before you get going on it. What do you notice that's conspicuously absent from this graph? 2 things. Yeah, what's one?
Time title?
The time on the x-axis. It should say time down here, and we're going to make that in seconds. You guys probably didn't even notice that, probably wouldn't have affected you, but that's what it's meant to be, time in seconds. What else is missing on this? What else should we always have on a graph, yeah? Okay, direction. We don't always see direction. If you don't see direction, then you just assume that it's the positive direction, whatever that is. If it's east is positive. If it's south, south is positive. The title, yeah. What would the title of this graph be? What should it be? Yeah, it should be position versus time. You know that it's position versus time because the y-axis always appears first and the x-axis appears second. What would be the responding variable on this? The position, right? It's whatever's on the y-axis. All right, let's see what you can do with this question, these questions now over the next couple minutes, and we'll take a look at it as a group. Let's go over this now. It says, use the graph to determine the position at 4 seconds. What do you do to find a position on a position time graph? Or a impulse on an impulse time graph? Or an energy on an energy time graph? What do? Up and over. So 4 seconds, we go to 4 seconds, we go up, and we go over, and it looks to be about 24 meters. 24 meters. Now, how many people said 24 meters? Did I say 25? I probably would give you the mark for that. Although you can tell that it doesn't quite go through the intersection point there. But is it 24? Is it 24 and a half? It's kind of hard to tell that. So in a case like that, unless it was more clear, I'd give you a little bit of leeway on that. Okay, 24, 25 will take you to one of those, or anything in between. The position at 7 seconds, all right, position at 7 seconds is also up and over. 7 seconds, we're going to go up and over. That's going to be exactly 30 meters. There's no uncertainty or ambiguity with that one. Exactly 30 meters. All right, next one. See, the displacement between 0 and 7 seconds. The displacement between 0 and 7 seconds. Well, displacement is final minus initial position. The final position at 7 seconds, we just established is 30 meters. The initial position at 0 seconds is just 0, so it's 30 minus 0, which is just 30 meters. The average velocity between 0 and 5 seconds. The average velocity, well, as I think it was Parker. Yeah, it was you that was asking this question earlier on. As Parker was saying, we could draw a line from 0 to 5 seconds. In fact, I think we might already have one drawn here. Yeah, we do actually. It's already a straight line. But even if it wasn't a straight line, you could draw a line from 0 to 5 seconds and then take the slope of that line. But the easiest way to do it, I think, when you're looking for average velocity, is just think of it as displacement over time. The displacement over the time. The displacement between 0 and 5 seconds, well, it's final minus initial position. At 5 seconds, we've got 30 meters. At 0 seconds, we've got 0 meters. So it's 5 meters minus 0 meters. No, it's not. It's 30 meters minus 0 meters. Over the time interval of 5 seconds, which is 6.0 meters per second. And what's the instantaneous velocity at 2.5 seconds? This is uniform motion. This is constant velocity. If the velocity is the same everywhere between 0 and 5 seconds, then what's the velocity at every moment of time in there, including at 2.5 seconds? 6 meters per second. So long as it's a straight line, the instantaneous velocity is exactly the same as the average or constant velocity. Make sense? You guys okay on a quiz on this tomorrow? Perfect. All right, on the board right now, you see another position time graph. This one is not quite as tidy as the position time graphs we've seen earlier today. No perfect straight lines. Rather, here we have some data points that are scattered a little bit. In fact, we call this a scatter plot because the data points are scattered a little bit. But you can see, if you look closely at it, that these points form almost a straight line. You can see that there's a clear trend that is upwards from the bottom left upwards towards the top right. This is not perfect constant velocity, but it's close enough that we could draw what we call a trend line or a line of best fit. We did that last week before the break, right? Remember, we drew the trend line for these scatter plots. I can't draw it on this because this is a spreadsheet, but what I will do with you is work through that process that we used the week before the break, of using your calculator and the stat function on your calculator to find the numbers that go with that line of best fit, particularly the slope of that graph. Make sense? Remember that? Remember doing that before the break? All right. This one is a particularly nice example because not only do we see the graph here with our data points, but we also have all of the data points listed. It's nice when we have a table because it's easier to get the numbers to punch into our calculators when we have that table given to us. If we don't, it's okay. All we do have to do is take the ordered pairs off of the graph. It's not the end of the world. It's just more work. That's all. What I want to do with you right now is go through this one. Using the data that we have given to us to get the slope of a line of best fit or a trend line for this. And then we'll do another example where we've not given the numbers in the form of a table. All right, so what I want you to do, I want everybody to do this. Take your calculators. Turn them on. And then I want to go through this procedure together here, okay? Listen carefully. It's a 6-word procedure. That's it. 6-word procedure. Stat edit 1, stat calc 4. Okay, repeat after me. Stat edit 1. You guys aren't very good at following instructions. Okay, repeat after me. Stat edit 1. Stat calc 4. Stat edit 1. Stat calc 4. Stat edit 1, stat calc 4. Stat edit 1, stat calc 4. Okay, now let's actually do it, okay? So right now we're on a blank screen of a calculator. Let's go stat, hit the stat button, edit 1. Stat edit 1. Right now I have some numbers up there. I want to get rid of those because I want to put in some new numbers. So I'm going to go up to the top of the columns. Right there, I'm going to press clear, and then I'm press the down button. When I'm on the header and I press clear and the down button, it deletes everything in my columns. So now I've got 2 nice empty columns, an X column and a Y column. Remember, stat edit 1 got me to this point. Stat edit 1 got me to this point. Now, let's enter my numbers. Yeah, I can enter from my table. If you don't have a table, then you just take the ordered pairs from your graph. I got 0.2, 0.42, 0.57, 0.83, 1.1, 1.15, 1.35, and 1.62. There's all my X numbers. Now it's time for my Y numbers. We got 9, we got 20, we got 33, we got 38, we got 46, we got 61, we got 68, and we got 82. Okay, there we are. Got all of them. Either it comes from your table, hopefully, or just ordered pairs from your graph. A little bit more work, but still both the same. Doesn't matter, you're at the same point. Remember, it was stat edit 1 that got us to this point. Okay, now that we have our data entered, what do we do? Stat edit 1, now we do stat calc 4. Okay, let's do that now. Stat, let's go calc, let's go 4. Stat calc 4. Now, depending on the version of the calculator you have, 83 or an 84, you might have to hit enter twice. You might have to hit enter 4 or 5 times. It doesn't matter. Just keep hitting enter until you have an answer here. Okay, enter twice for me. I get a slope of 49.99. Okay, that's the slope of my graph. And that should be exactly the slope of your graph since you use the exact same data points as I did. All right, having mastered this last question, let's see what you can do with this question this time. It's similar to the last one, except that this time you don't have a data table. This time you've got to find the ordered pairs. I'll go through a couple of those ordered pairs with you, and then you can finish them off and put them into your calculator. Remember, stat edit 1, stat calc 4. All right, first one, let's check our intervals first here. Kind of odd ones. Looks like we're going up by 0.1, 0.2, 0.3, 0.4. No, that's not it. 0.2, 0.4, 0.6, 0.8, 2. No, that doesn't work. What am I going up by here? 0.4, 0.8. So this is 0.8. And this is, well, we're going up by 0.4s on the y-axis as well. So it's 0.4, 0.8, looks like 1.0. Next one, it looks like we're going to 0.4, 0.8, 1.2, 1.6. Looks like about 1.8 and exactly 20. Exactly, yeah. That should be 0.8 and 10, not 1.0. See what I'm doing there, guys? See how we get those ordered pairs? I'm going to let you guys do the rest of those now, and then punch them into your calculator as stat edit 1, stat calc 4. Stat edit 1, stat calc 4. All right, do the rest of those and punch them into your calculator, see what you get. Let's finish this one up here now. We have our first 2 ordered pairs identified already. Let's identify the rest of them. The next one, I got 3.2 and 32. The next one I got 3.9 and 37. The next one I got 4.9 and 52. The next one I got 5.8 and 60. And the next one I got 7.2 and 68. Now, there may be a couple of yours that are off by a slightest little bit. It's hard to tell some of them exactly where the data points are supposed to be. And trust me, the answer accommodates for that or accounts for that. So in other words, the answer that we get, we'll accept a little bit of variation on either side of that, okay, just in case you interpreted a data point ever so slightly different than me. There won't be a lot of room there for error, but there'll be a little bit because, again, it's pretty difficult to tell exactly where some of those data points are. All right, technically we should have drawn a trend line or a line of best fit here, and that trend line should have looked something like this, although you should be using a ruler. You should be using a ruler, so it should be nicer than that. Now it's time to enter these into my calculator. So let's do this now. I'm going to go, what do I do? What are my first three keystrokes? Stat, edit 1. Stat, edit 1, enter. Now I got some data in there, so I want to clear those out. Remember, go up to the header, clear, press down. There it's clear. Now I'm going to type in my x coordinates, 0.8. I got 1.8. I've got 3.2. I've got 3.9. I've got 4.9. I've got 5.8. And I've got 7.2. There's my x's. Now my y's. I've got 10. I've got 20. I've got 32. I've got 37. I've got 52. I've got 60. I've got 68. Okay, that's all my points. Now what are my next three keystrokes? Stat, edit 1. Stat, calc 4. Stat, calc, option 4. Enter, enter. The slope of my graph is 9.4. You see that, guys? How many people got 9.4 for that? Or say 9.2 to 9.6. Anywhere between 9.2 and 9.6. Good. Good. That would be 100%. Got it? All right. Last thing that I want to show you today before we pack it up for the day is example number 7. This one is a position time graph. Once again, position on the y-axis, time on the x-axis, position responding variable, time in the manipulated variable. But this one is a curved line. What does this one represent if it's a curved line? It's speeding up. It's accelerating. The question asks us for the instantaneous velocity at 6 seconds. Now, if it was a straight line, we would find the slope of that straight line, or just use the equals d over delta t to find the constant velocity of that straight line. And the instantaneous velocity at any moment would be the same as that uniform velocity. But we can't do that here because this is accelerating. Now, what a lot of people want to do for this, they would be wrong, so don't copy this down. What a lot of people want to do is say, well, at 6 seconds, what's my position? 240, 280, 320? Why don't I just say, whoops, why don't I just say v equals d over t, 320 over 6. Remember, you're not writing this down because it's wrong. This does not give me the velocity at 6 seconds. The reason it doesn't give me the velocity at 6 seconds is because the equation for velocity is not position over time, rather it's displacement over time. I took a position and a time and divided them. I get the wrong answer. If I take a displacement and a time, I get a different answer. But what displacement do I use? When it's a curved line like that, what displacement do I use? Well, we have to draw what's called a tangent line. A tangent line is kind of like, almost like the path of a rock that you skip on a pond. Right? When you throw a rock at a pond, kind of try to skip it, right? It's going down almost straight and then skips off of one spot on the pond. right? It's not going through the water, it's bouncing off of one spot. The only difference between a tangent line we draw here and that rock skimming off the water is it doesn't change direction when it hits that point. It just keeps going in a straight line. So I'm going to say, I want to find the velocity at 6 seconds, right here. I want to draw a tangent line at 6 seconds. A tangent line that skips off of only that one spot. This is not a tangent line. You throw a rock at the water and skip it off, that's not skipping off, that's going into the water. So that's not a good tangent line. Okay, this is also not a good tangent line. Because that's not skipping off of that one spot, is it? That's hitting that one spot on the water and then going through the water. You see that? A good tangent line would look something like this. It's kind of hard to draw on the board here. You guys will have some more success when you're drawing it on a piece of paper with a straight edge. But it's going to look something like this. If I can move it now a little bit. It's going to look something like this. You can see that, look, here's the rock coming towards the water, coming towards the water, coming towards the water. Look, it skips off of that one spot on the water and then keeps going. Again, it's not changing direction like a real rock would do, but you get the point, I hope, is that it's skipping off of only that one spot on the water. Does that make sense? Notice I got a little bit of space in here. I got about the same amount of space in here. That's telling me that I've got a pretty good tangent line. If I drew it like this, that wouldn't be a very good tangent line because I'd have a lot of space here and no space over on the other side. Does that make sense? That's my tangent line. Your tangent line should be close to that, although I'm going to be honest with you, it's difficult, if not impossible, for everybody to get the exact same tangent line. They should be close, but they're not going to be perfect. Okay, the answer key will reflect the probability that everybody's going to have a slightly different answer. All right, what do you think I'm going to do with this now? What do you think I'm going to do with this? Sorry? Slope. Yeah, you use slope or delta D over delta T. Pick 2 points. Let's pick a point right here. Let's pick a point right here. The slope of this is, well, I say delta y over delta x, which is really just displacement over time, right? Displacement, final position minus initial position, over final time minus initial time. My displacement is going to be what? I think I'm right here. 400, 440, 480, 520. Looks like about 530. $540. I think it's about 540 actually. 540 minus 0 over 8 seconds minus, what is this going to be? 2.4, 2.8, 3.2. So 540 divided by 4.8 seconds. $540 divided by 4.8 gives me a value of, I got 113. Please do this for me right now. I'm not going to give you any homework on this. Just do this for me right now, okay? Draw your line of best fit. Don't copy down my slope calculation. Do your own slope calculation. When you do, you should get a number that's close to 113. It's going to be off by a bit probably, but if you get probably anywhere between about 108 and 118, I would give you credit for that. Okay, plus or minus about 5%-ish. Okay, give that a whirl for the next couple minutes in class here and see what you can get.